Hello, and you're listening to a special edition of The Naked Scientist. We're here at the Cambridge Science Centre with our wonderful studio audience. And we're ready to discuss some amazing engineering today, from levitating trains to earthquake-proof buildings. And we've got some brilliant panellists of engineers here to answer your questions. I'm Ginny Smith, and my panel are going to introduce themselves now, so let's start from that end.
I'm David Cardwell. I'm Professor of Superconducting Engineering here in the Department of Engineering in Cambridge. I head the bulk superconductivity group, and we make materials that have got amazing properties. We're going to demonstrate some this evening, but they generate large magnetic fields in a very stable way, and there are a number of exciting applications just around the corner.
My name is Sinan Chikos. I am a PhD student currently at the Department of Engineering. I work on earthquake-resistant structures. Earthquakes are a fairly common hazard at some parts of the world, and we need to make sure that our structures are resilient, and we work on a particular type of isolation system, which is rocking.
Hi, my name's Lucy Fielding. I'm a postdoctoral researcher at the Department of Materials Science and Metallurgy, working with the Rolls-Royce group there. And my area of expertise is super strong steels. So I'm interested in understanding what gives these extreme materials the properties that they generate so that we can use that to design even more extreme materials. Because, of course, all of our extremely advanced technologies are only ever going to be advanced as the materials we make them out of. Studying materials engineering is a really crucial part of that design cycle.
Hi, I'm Kirsty Kuo, and I'm a research associate in the engineering department working on a climate engineering project. And climate engineering is the idea that we could artificially alter our climate in case global warming happens really severely. And the idea that we have is to build a giant hose pipe up to 20 kilometers in the stratosphere, and through this hose pipe we could pump reflective particles. These reflective particles could block the sunlight and cool the Earth.
So get your thinking caps on for questions for any of our experts. Also with us today, we've got Dave Ansell and Kate Lamble, who are going to be doing some fantastic experiments for us. Hi there, guys.
Hello. I'm either going to be levitating in front of your very eyes or losing a toe to liquid nitrogen. It's 50-50 at the moment. We'll see what happens.
And I'm going to be looking at some of the properties of steel and making some little earthquakes to see what happens to buildings.
Fantastic. So can we have a round of applause for our brilliant guests and experimenters tonight, please? So first of all, we're going to start with you, David. Now, you're Professor of Superconducting Engineering, but what is a superconductor?
A superconductor is a material that, when you cool it below a certain temperature, it loses all resistance to the flow of electrical current. So you can either get very big currents down your superconductor, or you can use that current to generate very big magnetic fields. The currents are bigger than you can get down any conventional material, and the fields it produces are bigger than any other source. So things like, anybody's ever had an MRI scan, that field would have been generated by a superconducting coil. You just can't achieve those fields using conventional metals like copper.
And what other kinds of applications are they used for at the moment?
There are three different types of superconductor. You either make them in long, thin conductors where you can pump current down, you can control it. Because the material is superconducting, for a certain type of current, there's no loss. And a significant amount of power we generate is actually lost by heating wires, 10 or 11%. If you could make your cable superconducting, then we'd get rid of all that loss. So there are big energy efficiency gains. You can make them in the form of bulk materials. Some people call them hockey pucks. And you can use those materials like you'd use a permanent magnet. But the field you generate is a lot bigger. And the final is a thin film form. So that's a very small amount of material, but with very good properties, and you can use those in things like electronic applications, microwave filters, generators, basically the electronics small-scale industry. So different range of material forms, each of which has its own benefits for a specific type of application.
So you mentioned these bulk ones that look like hockey pucks. Is that what you've got in front of you there? I can see something that looks
absolutely.
Like.
So what I'll do is I'll demonstrate the properties of a bulk material. So what happens is, if you have a magnetic field, and I've got one here, it's a speaker magnet, and I'm going to bring the superconductor towards the speaker magnet, and we've got this thing called Faraday's law, and that tells you that will cause a current to flow. The current will generate a magnetic field, and by Lenz's law, that field will be in a direction to oppose the change that's causing it, GCSE physics. So as I bring the superconductor down, we'll get this current established. If it were copper, that current would decay away. The superconductor's got no resistance, so when the current's induced, it continues to flow, it persists. So the field it produced persists, and therefore you get a levitation force, a repulsion force. So if I just bring the superconductor down now on top of the magnet, You can see it's levitating away right above the superconductor there. And it will stay there until it actually warms up through its transition temperature. This is about minus 196 degrees. When it gets above its transition temperature, then it becomes non-superconducting and it'll lose its levitating properties.
So those two magnets are repelling in the same way that if I got a pair of bar magnets and tried to bring the north poles together, I would be
Yeah.
able to feel a force. Is that the same
It's
idea?
exactly the same force, except if you tried to bring two bar magnets together, you wouldn't be able to levitate one on top of the other. One would flip round and north would attract south. So there's an intrinsic instability there. So one property we've demonstrated with a superconductor here is that you get this stable levitation, and that's something you can't achieve with permanent magnets.
Now that's cool, but it's not very useful levitating a little hockey puck size thing. Can we use that for anything more practical?
Right, so basically the properties we're interested in goes magnetic field squared. So if you can double the field, you get 4 times the levitation force, 4 times the energy density. Since we've got stable levitation, an obvious thing is a maglev levitating train on a bigger scale. There's also a very strong field gradient here, and you can use that to separate a magnetic species from a non-magnetic species. Down the line, using these materials in motors and generators, so you get much bigger fields than you can generate with steel, for example, or iron, and therefore you can throw the iron and steel away. And some people say you can get
Lucy's getting quite cross with you
about
saying
half
that.
the volume or weight.
So we don't have a train that we
No.
can levitate today, but we do have a Kate.
We do.
Can we have a go at making her levitate?
There's a big box in front of me which is white, and there's a lot of smoke coming out of it, and I can see sort of ice crystals forming around some of these screws that are holding it together. It looks quite intimidating, David. What's going on in this box that you're asking me to
Right.
stand on purely from faith?
So we've got every confidence in you there. So we've got an array of these bulk superconductors, and the platform on the top, at the back of it, we have a ring of permanent magnets. And when the permanent magnets meet the superconductor, they're levitated. It's just the inverse of what we've done here. Now, if we try to bring the magnets closer to the superconductor, additional currents will be induced and that will be resisted. If we try to move the plate from side to side, we're changing the field at the surface of the superconductor, it will try to resist that. However, the plate's got circular symmetry, so if we were to rotate the plate, the field at the centre and the surface of the superconductors is constant, so there's no resistance to that motion whatsoever. So the bottom line is the plate won't move up or down very much, it won't move from side to side very much, but if we try to spin it, there's no resistance.
So I'm not going to float across the room, but I could get dizzy, is what we're saying.
We could make it into a linear motor, not tonight, but another time we could. Then you might float across the room.
If only. Is there any chance that I could be too heavy for this? Is there a reason that I'm doing it
Right.
rather than, say, Dave?
So the levitation.
No offence, Dave.
I'm glad you said Dave and not me, actually. Like all forces, if you apply force that's equal and opposite to the force that's supporting you, you will overcome it and the thing will collapse. But I think it's probably about 1,000 newtons at least that you'd have to apply. So 100 kilograms it ought to support.
Okay, so basically I
I
shouldn't
think you
be
should
too
be
fat for
okay.
this.
Yeah.
Okay,
My money's on you.
let's give it a go. I'm having to get Dave to hold the mic so I don't spin around. Okay, so immediately I'm spinning. So I did promise the people levitation tonight. Dave's going to have to follow me around in circles with the microphone here. Now,
You need to push on something.
It's
so
not
push.
a very good magic trick. It's not like I'm basically being dynamo off the telly and I'm floating meters off the ground. By how much am I levitating currently?
It's probably about a centimetre.
About a centimetre.
Yeah.
Okay, let me give it a spin. Okay, I'm getting really... So there's no way of it stopping, basically. That's what we've established.
Well,
from that
eventually it will stop.
experiment. How long is it likely to take?
We could wait till it warms up.
We could wait till it warms up. How long is that going to
Be about 40 minutes.
40 minutes of spinning. I'm not sure I can last that long. I might have to push in the opposite direction. I am genuinely dizzy right now. We're going to have to just wait a moment. So, this is awesome, but we said that trains might be useful. Do trains use exactly the same system, or is it adapted slightly for humans?
It's the same principle. A train might use 4 of these and a linear rail rather than a circular track. So you'd get linear motion just in the same way that you've got circular motion here.
My feet are currently getting cold because there's a lot of
Yeah.
liquid nitrogen underneath me right now.
Yeah.
Now, you mentioned it wouldn't work when it warmed up. So are we having to permanently pour liquid nitrogen into train tracks to get maglev trains to work?
Well, you can cool things electrically, so you need a power supply rather than a vat of liquid nitrogen. So there are other ways to cool it, but they're not as spectacular as this way.
It's not spectacular. I'm not sure how I'm ever going to get off this. I could be stuck here for the rest of the show.
For Kate, as she attempts to climb back down. So we've just said that you need a big vat of liquid nitrogen to cool this. I guess that's probably one of the big limitations that's stopping us from using superconductors in more things nowadays. Is that something you're working on?
I guess the question I'm asked more than any other is what temperature do these materials superconduct at, and will we ever get room temperature superconductivity? There are two solutions to that. One is, if you're a physicist, it matters because that tells you about the pairing mechanism, what's causing superconductivity. If you're an engineer, you're not really bothered about that. You're bothered about how much current can it generate, how much fuel can it produce. So we work with the best materials we have, which just happen to be the ones that we need to cool to these low temperatures. But in a real application, as I said, you wouldn't need a liquid cryogen. You'd use it's like a high-tech fridge. I mean, you don't pour a cryogen in the back of your fridge to keep your milk cool, yet you can maintain a freezer at minus 25. So you can use a glorified fridge, it's called a Stirling cycle cooler, and you can actually achieve 20 Kelvin, so well below this temperature. But it's not something you'd find in a vacuum cleaner, for example. But it might be something you find in an industrial plant that involves moving heavy masses across a workshop floor. Boeing may levitate their aircraft on their production line using this technology one day. We don't know.
Now, we're going to go over to some questions from the audience in just a second, so get your thinking caps on. But first, Kate, have you got a question that came in on social media?
Gerald McCullen on Facebook, we've just mentioned maglev and things like that. He said, whatever happened to levitating trains? He doesn't think they're still around.
No, there are. There's a fairly well-documented train in Japan using low-temperature superconductors, not liquid nitrogen temperature, but liquid helium temperature superconductors. There's one in Shanghai from Pudong Airport to downtown Shanghai. There's a couple in Germany, so they're around. The problem is the track's expensive, as you can imagine. So you're looking at least an order of magnitude more expensive than a normal train. But you can travel at speeds of getting up to 500 kilometres per hour.
So who's got a question about superconductors and high-speed travel? We got one down the front here.
Hi, I'm Anastasia, originally from Russia. I wonder, how do they break those trains?
Essentially, there's a jet on the train. The superconductors give you levitation. If you have a clever arrangement, you can get a bit of propulsion, but essentially all you're using the superconductors for is a frictionless platform. It's low temperature flying. So like an aircraft, how does an aircraft go forward? Well, thrust is provided by the jet engine, so you need some onboard mechanism of propelling. A big fan on the back of the train might do it.
My name's Sam, I'm 12 and I'm from St Ives. You said if it warms up, it will stop spinning. If you had a train going straight, if it warmed up, would it just suddenly stop halfway through a journey? If it
we
warmed up?
wouldn't want that to happen, would we? That would be a problem. So what you do is you have a fail-safe mechanism. So you wouldn't just rely on levitation. You'd have a wheel-based system. So if it warmed up, and it doesn't warm up quickly, as you saw with the demonstration, it warms up slowly. And as it warmed up slowly, the train would get lower and lower and lower, and then it would land on its rails and it would carry on. So it would then go on its wheels rather than being magnetically levitated. At that point, you would have slowed the train down. It would be a conventional system.
I'm Gareth. I'm 12 from Huntingdon. How many years do you think it will be before we actually get levitating trains or other vehicles?
We've been saying 5 years for about 15 years. But I think reality is that we are getting very close to applications, and I don't think they'll start with levitating trains. I think they'll start with smaller devices that do very unique, very niche things that we can't do using anything else. I think levitating trains may be where we get to eventually, but to begin with, I think we need to do things that use our imagination that we haven't thought of before. And we're working on a number of devices that do exactly that right now. And the turnaround time for those devices are about 2 to 3 years. So I really believe that in that timescale, we're going to get commercial applications of these materials. Whether it's levitating train, I doubt, but sometime in the future, almost certainly levitating trains as well.
Hi, my name is Danny, and I'm also 12 I'm originally from Syria, but I moved to England. And I'm asking roughly how cold is liquid nitrogen and what material are they planning to use for levitating trains?
Okay, so liquid nitrogen is 77 Kelvin. If you look at the Kelvin scale, absolute zero is minus 263 degrees C. So it's pretty cold. So 77 Kelvin is minus 196 degrees C. I gather if you go to the very north of Finland, you're approaching room temperature superconductivity because it's pretty cold up there, but not quite that cold. So it's minus 196 degrees C. That's the temperature that we operate these materials at, or lower. The lower in temperature you go, the better the performance. And your second question was what material? Well, these materials they look black. They're ceramic in nature in terms of properties, and they're a mixture of a complex mixture of elements. So this one is yttrium, barium, and copper with a bit of oxygen in there. So yttrium, barium, copper oxide, and that's the basic material. You may change the yttrium, but you will have the barium, the copper, and the oxygen there. So yttrium, barium, copper oxide. We make them in a furnace at about 1,000 degrees C.
That's pretty extreme. So I think we've got time for one more question. This gentleman in the white shirt had one.
Hi there, James, 28, a bit older than the rest of the guys.
You don't look
from
it.
Cambridge. I think you almost solved your own question about how you might do levitating trains, because it's expensive, but on the long sections of track where in the countryside, you could levitate the train. And then, as you said, when you get into train stations or near cities, you could just lower the temperature down, and then they could just run on their tracks.
Yeah, you could. The problem is you've got a thermal mass, and you can't. With transport, you've got to have instant changes. So you can't wait 3 minutes for something to warm up. And I think the way to do it is not to warm it up, but it's to divert the field. So you do something else with the field. Or in this particular case, if you're moving at a high speed, you've got a high field rate of change. That induces another field, and therefore you get levitation. So when you slow down, it will land automatically. That's the best way of doing it, but the cost is still in the track, and it's hugely expensive. If anybody who's ever been on the Shanghai maglev, just looking at the track, it just oozes yen. You can see it, and it's hugely expensive.
Brilliant. Thank you, David. That was Professor David Cardwell, who's Professor of Superconducting Engineering at Cambridge University's Department of Engineering. Now, next up, we've got Sinan Achikos, a PhD student in the Structures Group at Cambridge University Department of Engineering. And he's looking at ways to make buildings resist earthquakes. So, Sinan, why are earthquakes such a big problem for buildings?
Well, there's a very important saying, which I think belongs to Nicholas Ambrosius, who was a very big, important man in our field. And he said, earthquakes don't kill people, buildings do. And I think this lies at the heart of the issue, that we all live in buildings, we all need civil structures to actually sustain our society, and we need to protect them from earthquakes. And earthquakes happen over hundreds of years, they don't stop, and our Earth is going to keep on giving us shakes here and there. So we need to be prepared for these important events. And they're very costly when they happen, even when we actually manage to stop buildings from collapsing, stop deaths occurring during earthquakes. They can be very costly, and they can be, if that happens on a regular basis, that can be very damaging economically.
Are there some buildings that are more susceptible to earthquakes than others? I mean, I imagine the sort of really tall skyscrapers you see are probably more dangerous than old-fashioned sort of lower houses?
I'm not so sure, because it's a complex issue in the sense that when you make a structure which is small, compact, stiff, that structure will end up attracting more load. And actually, the structures you mentioned, the skyscrapers, they're all engineered structures. And it's actually quite rare that you would find them in places where there's a recurrent danger of earthquakes. So there would be building regulations which would actually limit the number of stories, or suggest that there should be technologies in place to actually prevent these buildings from moving a lot. So actually certain buildings are certainly more susceptible to earthquakes. For instance, masonry buildings would be one example, and a recent earthquake that happened in Christchurch, for instance, was a good example of this, where the city centre, where the earthquake hit a city centre, and city centre was full of beautiful old masonry buildings. You must have all seen the Christchurch Cathedral after the earthquake, and it was in shambles. So certainly there are structures which are more susceptible, and these are generally structures which are not engineered to withstand earthquakes with modern science.
So what can you do to make a building more resistant to earthquakes? Do you build one that won't move when the earthquake happens, that'll just stay nice and still so everyone inside it's safe?
That would be great, because if we had something that's rigid, if the ground moves, if you've got something that's sitting on a ground and it's completely rigid, the accelerations in that building will not exceed that of the ground. Whereas if you've got a flexible structure, imagine a very tall skyscraper, as you've given an example, that building actually will amplify its motion. At the top stories, you will get a lot of sway. And the strategies that we can do is actually we can design our buildings to be completely elastic during an earthquake, which is the earthquake will happen just like, you move a rubber band, you pull it back, you leave it, and then it comes back to its own original state. So we would ideally like to do that. We would ideally like to have a building which doesn't get damaged, but that's just far too expensive. So what we do instead is we try to decouple the structure from the motion of the ground during an earthquake. So that would be called base isolation. That's one strategy. And the second strategy is what is really commonly adopted today. You let the building get damaged during an earthquake, which is quite counterintuitive to people because one would hope that an earthquake-resistant building is damage-proof. But what happens is this damage that occurs in a building is actually what saves the building. So this is another strategy, but what earthquake engineers want right now, what is our biggest challenge is actually making structures which are safe during an earthquake and which do not get damaged. And it's actually a big challenge.
Now, I've never actually been in an earthquake, so I'm finding it quite difficult to kind of imagine what happens to buildings during one. So, Dave, you've got something over there that's going to show us a bit more about how it would actually look if you were in an earthquake. A very, very small earthquake.
Yeah, Dave's been building something all week. What have we got here, Dave?
Basically, what I've got here is a platform which acts like the ground, which if I turn it on, wobbles. And it's basically like an earthquake. And I can change the speed of that wobble. And so at the moment, it's wobbling quite slowly, and the building is behaving fairly stiffly, and it's just moving with the ground. And you'd probably be perfectly happy in that building. But if I change the speed a bit faster...
So this is the ground shaking more quickly.
As you see now, Kate, the building is starting to, it's bending.
It's buckling under the thing. It's no longer shaking just in line with the earth moving. It's sort of bending in the sections in the towers.
So basically, buildings can have a natural speed at which they want to vibrate. And if there's a very strong speed, which is called resonance, that the building wants to vibrate at, and if the earthquake happens to hit that, the vibrations get bigger and bigger and bigger, and you get into real trouble. So I imagine designing buildings to avoid the resonance being anywhere near an earthquake speed is very, very important to them.
This is something that's quite important that we try to actually take care of in our research. So the concept of base isolation that we just discussed is essentially actually just this. So there's a frequency range during an earthquake, which the ground will move. And you want to move away from that frequency. You want your structure to be away from that frequency so that the motion doesn't build up. So the typical example of a resonance is if you're pushing somebody when they're in a swing. So the motion will just build up, build up, build up, and that will be too dangerous. So what we try to do in a base-isolated building is actually put something very soft underneath the structure so that its frequency will just go very low. And actually, this will decrease the loads that is acting on the structure.
I remember the Wibbly Wobbly Bridge in London. When it first opened, the Millennium Bridge, it was meant to be this huge thing, and then sort of as soon as people marched over it, it started shaking, and that was because people were marching over it in the same resonance. Do all earthquakes have the same resonance, though? Can you predict at what sort of frequency it's going to be shaking about?
Well, this is actually a field where there's a lot of research as well. We try to characterize earthquakes, but you cannot really specifically guess what a specific earthquake is going to be like. So we need to actually design it for a specific range of frequencies, large range of frequencies, and be very conservative about how we do it. So what happened with Millennium Bridge was a very interesting example because the lateral frequency of the bridge actually really matched what the frequency of the people would be walking in, which is roughly about 1 hertz. So this is a very specific example. With buildings, interestingly, the frequency actually falls in the range where the earthquakes would be most damaging. So especially for short, stocky structures, this is a big, big danger that we have. My personal research about earthquake engineering actually works on structures which are rocking, and these rocking structures are slightly different because we let them separate from the ground during an earthquake. So the common strategy is you would just tie down a structure to the ground, and you would not let it separate, so it would eat up all the energy of the earthquake. Whereas if you let a structure separate from the ground, it will actually take the earthquake energy, and there's actually a setup there which we're going to be demonstrating. It's over there.
So Dave's model is about the height of my hand, but this one's a little bit larger. So what are we going to be showing with this model?
So this is a 3-story shear frame, which is a normal building frame. It's bare, it doesn't have all the other non-structural components. But what would happen is, let's say there's an earthquake, and if the building is fixed to the ground, it would start to shake, and the building will actually start to take all the load. It will start to vibrate. But what we propose is, instead of, and this idea is not actually our proposal, it has been around for a long, long time, is actually if you let the building separate from the ground during an earthquake, it will just, if you push a structure like this and hold it from the base, you can see that the columns are all taking all the load. And that's actually quite heavy on the columns because we have to design them for bigger forces. But if the structure is rocking, and if you push it, what will happen is it will take the load, but the load will be actually translated into movement. And this movement is actually causing the structure to have less load because it's more flexible and it's easily ready to move. And the concept of resonance that they've mentioned. So if you move something really far away, this has got a very big motion.
I'm sorry, Sinan. So when you pushed it and held it down to the ground, I could see that the columns were bending. But to me, literally rocking the building, tipping half an edge off the ground and then sort of letting it tilt backwards. If I was in this building, I'd rather have the columns bend. Is that the wrong way of thinking about it? Just looking at this tilting at a 45-degree angle here?
Well, that's... personally, I've never been in one of these things. I would like to be. And it's so much easier working on paper. But the interesting thing about these is normally, if you're in practice, what would happen is instead of these fiddly little bits that we have here, which restrain the structure, which restrain the shear frame down, we would have big steel members, steel tendons, which would run through the structure and hold it down. So actually, we would be allowing only very small motions. In terms of percentage, it would be only 1% of the height of the total building. So very, very small movements we would allow. And you would probably not be able to tell the difference in between a structure which is rocking and which is not. And the interesting thing probably is that when you're in a structure which is rocking, yes, you would feel the low frequency motion of the structure going from the left to the right. You would feel this. But there would be actually less acceleration of the stories doing this fiddly motion. So you would actually decrease the loads on the structure. And that's sort of the interesting thing, because that causes the loads to be less. We can design the structures to be more economical and more resilient actually during an earthquake, because they don't get damaged.
So by allowing it to tip from one side to another imperceptibly, if I was inside this building, you're putting it under less stress, and that means that in a big earthquake it might get less damaged.
Exactly, that's the case, because as I said, the current methodology that we have, we allow buildings to get damaged, and this is not good for the long term, because after an earthquake there are millions and millions of dollars of damage, and this is very bad for the economy, and we want our structures to be safe.
So basically you're saying, I'm wrong, I want to be in the rocking building rather than sort of the wibbly wobbly one. How can you be sure, if you're allowing it to sort of tilt to one side and then come back down again, that it will come down in exactly the same place?
So that's a very important part of the research that we do. What we want to do is we want to restrain these structures. So we don't let them fiddle about. As you can see from this model, when it actually rocks, it starts to walk off from its foundations, which is quite dangerous. So we want to keep it in place. And the way we do it is, as I said, we would have large tendons which run through the structure. We would have other restrainers, other energy dissipators, which would dissipate the earthquake energy coming from the ground. And these would actually restrain the movement. So that's one thing that we would engineer.
Right, who's got any questions for Sinan?
I'm George, I'm 10 and I'm from Ely. Do you really have to make the buildings earthquake proof? Because an earthquake is caused when two plates crush together or they overlap. Couldn't you just prevent that somehow and then you wouldn't have to have earthquake proof buildings?
Good question. Why can't we just stop earthquakes? Come on, guys.
That's an excellent question. And I think that would actually be a solution to all the problems, really. But the motions of the Earth are very big. So these forces of plates moving are massive. And when they create these earthquakes, comparing an earthquake force to, let's say, to a Hiroshima bomb, you can see actually, I don't really have the numbers with me, but you can see actually how big an earthquake force is. And it's an unstoppable force. It would be great if we could actually stop it from the beginning, but these earthquakes do tend to happen, and they create these, as you have said, they're plate motions, and they create these big mountains, so you can imagine what sort of big forces we're talking about.
The Earth's still more powerful than a scientist at the moment.
Hi, I'm Vinod, and I'm from Cambridge, but I'm originally from India. While growing up, I did experience a couple of earthquakes, and the major one was the 2001 in West India. That was 7.7 magnitude, I think, and there was a lot of destruction and loss of life and property, but the main thing was the capital near my city. There wasn't much destruction, but there were 50 multi-story buildings collapsed because there was absolutely no earthquake planning there. One of the major local rumor was that few buildings collapsed because they had a big swimming pool on the top. Was there any truth to that, or does that affect if you have a really big water body on the top of a building?
Well, this is a very interesting question. I would imagine this might not exactly be true, because it's actually at the top, so probably what happened was, if there was collapse, especially, was probably related to lower stories. In most of these cases, in recent earthquakes in Haiti, for instance, where there was massive damage, one of the things that earthquake engineers realize is, during these earthquakes, We are not currently learning sometimes many things new because we actually have the technology to withstand the earthquake, but it sometimes boils down to actually having the regulation, doing it properly. And this is a very big problem, and especially in the developing world where an earthquake can still actually cause very big damage. Whereas in developed nations, for instance, when the earthquake happened in New Zealand, life safety was actually reduced to a minimum. And this is quite an achievement in terms of what we've done, but in that case, the damage, economical damage, was just beyond control. So we have to manage both of these ends, and that's a very big task, I think, which extends beyond earthquake engineers, goes to policymakers and beyond.
Hi, my name is Justin. I'm from Cambridge. I have a question for both the first speakers. Would it be possible to use superconducting technology to act as maybe dampeners or motion restrictors for earthquakes?
Could we levitate our buildings so that the earth just moves underneath them? That sounds like a brilliant idea.
It's a great idea, and it has been suggested, but it's completely impractical. The best way is, I think it's a guy called Robinson designed the building isolators, specifically, I guess, after Christchurch earthquakes, but it's much better to have a rubber viscous damper rather than something that's levitated.
Taking the fantasy further, I think we would actually want to lift the plates up so that they don't crash into each other, so that there's no earthquakes. But
levitate the Earth's whole plate? I think that might need a very strong magnet. Okay, I've got another question in the front row.
My name's Jess from St Ives. You spoke about partially destructive structures. Did you give an example of that? Because I didn't appreciate that.
So when I say partially destructive structures, so imagine just an ordinary reinforced concrete frame, which is currently designed, again, going back to this Christchurch example, many buildings just after the earthquake, which was conventionally designed, which is just structures which are fixed to their ground, which don't uplift, as in the example that I've illustrated, which don't have a base isolation at the bottom. So these buildings just get damaged. And when I say damage, this is all controlled damage. So what would happen is first the beams would get damaged, and then slowly they would migrate to the columns, because we designed beams to be weak so that they can dissipate the earthquake energy, because they're not as essential as the columns. So they get damaged first, and then the damage would migrate to the columns. And in the meanwhile, the building is supposed to stay intact. But in terms of damage, when I mean damage, you would see cracks on the building, you would see big cracks on the column and beam interfaces, and this is all stuff you would expect. And on top of it, after an earthquake, if it has gotten to this level of damage that it cannot be repaired, which is very common because if you imagine a reinforced concrete building again, it's got steel bars running through it. So how are you going to be actually removing those steels which have yielded completely during the earthquake without taking the column out and without replacing the whole structure? So it becomes a very difficult issue. It is actually, as I said, very common way of designing structures, and it will just happen to any ordinary structure that you can imagine.
That was Sinan Achigos, who's a PhD student in the Structures Group at Cambridge University Department of Engineering. You're listening to a special edition of The Naked Scientists from the Cambridge Science Centre with our wonderful studio audience. Give us a round of applause. Next up, we've got Lucy Fielding, who's a postdoctoral researcher at the Cambridge University Department of Material Science and Metallurgy. So, Lucy, you work on super strong steel. Now, steel kind of feels like it's been around forever. Are we really still finding out new things about it?
Well, as my supervisor used to say, the universe has also been around forever, and we're still finding out new things about it. So you should never underestimate the new things that you can still discover. One of the wonderful things about steel is that because we've known about it for so long, because it has been around for so long, and I think the oldest steel artifact that's ever been discovered is about 3,500 years old, so that's older than Stonehenge, is that we've had a long time to try and understand it. And that means that we're much more advanced in terms of where we are, because we've had all of that preliminary work done for us back in the last century.
So what exactly is steel? I mean, I know it's a metal, but it's not on the periodic table, is it? It's made up of some other things.
No, exactly. So steel is actually a mixture of iron and carbon, so it's an alloy. And you can also add in other elements to do different things. But in reality, what you have is you have pure iron that contains 0% carbon, and then you add a little bit of carbon in, so maybe anything from a very small amount to moderate amounts, like maybe 4% carbon. You might get away with calling that steel. If you keep adding carbon, it goes back to being iron again. which is a bit odd, but we've got through a small window. Iron with a little bit of carbon in is steel.
And why is it so useful? Why do we use it for so many different things?
Well, there's two reasons, really. One, it's cheap, and two, it's everywhere. Iron is pretty abundant in a lot of places around the world, and that is what, in a sense, makes it cheap. It's relatively easy now to extract, it's easy to work with, and it's also able to be recycled. So we want to try and use it for as much as possible because of its cheapness, because we don't have a problem with running out of it.
Now, you said you work on super strong steels. What do you have to do to this stuff to make it that strong?
Well, you can do quite a lot of things. Fundamentally, and we have to understand what strength means when we talk about metals. When we say strength, what we mean is how much force can we apply to it before it permanently deforms. So we have to understand what happens when that metal deforms. And on an atomic level, what is essentially going on is the atoms are moving relative to one another. Now, in a regular metal, well, in any metal really, those atoms are bonded together. So if you're going to start making them move past one another and change their position, you're having to break through all those bonds. And that's what requires you to apply a force. That's what requires you to put energy in. So what we try and do as metallurgists is we try and find ways to stop the atoms being able to move past one another so easily. So one method might be to actually try and deform the material a lot, because then the atoms move around a lot. They get all jumbled up. They get in each other's way, and it becomes progressively more difficult. Another method might be to mix in other elements, so other atoms of different shapes and sizes. So carbon is one. Typically, high carbon steels will be stronger than low carbon steels, but you can also add in other elements like aluminium, like silicon, like chromium. Suddenly you've got atoms all different shapes and sizes everywhere, and again that makes it difficult. And we can even do something called precipitation, and that's when we try and make a second compound appear inside the first compound. So you might be familiar with precipitation. We dissolve salt in water while it's hot, cool it down, and the salt starts crystallizing out. And you can do something a little bit similar with metals. And these blobs of precipitate of a second compound will get in the way of the atoms and stop them moving. And I think Dave's got some little experiments to illustrate how we can change the behavior of a steel with some fairly simple techniques.
So at the moment, if you're in the audience, we should have some paper clips being handed out.
So these aren't special paper clips. They're not special science paper clips. They're just normal ones that anyone could buy.
These are just perfectly normal paper clips. What I want you to do is just sort of stretch your paper clip out a bit so you can get at it. So it's forming a bit of a kind of a quadrilateral. So just stretch it out so it's not overlapping itself anymore. Now, what I want you to do is we're thinking about distorting this material. So Lucy was talking about how materials get stiffer as you distort them more often. What I want you to do is pick a straight bit which hasn't been bent already, and then just between your fingertips, so bend it about 90 degrees, make a really nice sharp bend around one of your fingernails, and try and feel how hard that was. Remember how hard that was?
Just remember to do it with your fingertips, because I was doing it earlier, sort of brute force, because I need that for a paperclip, and I couldn't feel anything.
So just bend it around one of your fingernails. Remember how much force that required. Now bend it back again and see if it's harder or easier.
Quite a lot harder.
So Dave, should that have been harder, or are we just getting weaker with every bend?
So that should be getting harder. The more you bend steel, certainly to start with, there are little imperfections which the steel uses to bend more easily, and they all kind of get locked up. And as you bend it, it gets stiffer and stiffer and stiffer. If you keep on going, this material gets stiffer and stiffer and stiffer until it will break brittly and snap like Junior.
Break.
So if you do it too often, then the material just gets weaker and weaker, and as it gets more and more brittle, the only way it can change shape is to crack, and that's really bad because your steel gets weaker. So that's kind of dull. But one of the other reasons why steel is really, really important is it's not just the material itself and how you bend it, which affects its properties, it's how you heat it.
Yeah, I can see you getting out a blowtorch here, Dave. We haven't got a blowtorch under everybody's chair. I'm very sorry. I wanted to, but health and safety got in the way. So we'll light up the blowtorch.
And so I'm going to heat up this paper clip.
The flame's going a different colour. Should that be happening?
So basically what we're doing here is a flame test. So there's a little bit of sodium on from my sweat of my fingers, and that makes the flame go orange. But the steel itself is now going orange.
So it's glowing sort of red hot, as I'd call it.
And I'm just going to let it cool down. It's actually orange hot. I'm just letting it cool down to room temperature very slowly. If you do this at home, beware that it stays hot longer than you think it is, because it looks like it's not red anymore, but that doesn't mean it's not hot enough to hurt you. I'll just put it in some water. Yeah, it's plenty cold enough. And now, Kate, try bending that.
Oh, it's really, really sort of soft and malleable and sort of squidgy. I've got also burnt bits all over my hands now. So it's, if I compare it to the other bit, it's a lot more effort, whereas this bit is sort of really soft and squidgy. Should that have happened, or have you just destroyed the paperclip?
When I heated it up and let it cool down very, very slowly, that means that all of these imperfections, as they get hot, they kind of relax back to their normal state, and then they can move really easily for a while. As you bend it, as you get stiffer and stiffer and stiffer until it gets really hard to move again.
So Lucy, you work on super strong steel, so you're not going to want to do what Dave just did and heat it up to make it really soft, but what kind of applications are you using these steels for? Why do you want to make such strong steels?
Well, first off, you're a little bit wrong in that we always want to heat up the steel to make it soft. This is a very common first step in steel production, getting it hot, because when you see steel products, they are not in ingots, the shape that you might get them when they're being cast. You often get steel in the form of plates, in rods, and I'm sure that Sinan's familiar with I-beams and other structural forms of steel. So you actually want it to be soft so that you can change it into those shapes very easily. The other reason that we want it to be soft is because it's a good first step when we're producing more complex structures to just heat it up so that it's nice and soft and uniform, and then we can cool it down at different rates and we can create much more complex structures. And these kinds of structures are immensely varied, and honestly, I mean, you can use it for quite a lot of applications. So we see applications in oil pipelines, oil rigs, in nuclear submarines, and the nuclear industry uses a lot of steel. I work on high-strength armour steels at the moment. Another very common application for steels is bearings. So bearing steels are very, very common. Some of the most efficient high-performance bearings in the world are made from steel. And lastly, jet engines, which is a fact that not many people know. So you're very familiar probably with nickel superalloys and things like that that are used in the most advanced jet engines. But many people are unaware, including, sadly, some people who actually make jet engines, that the central shaft of the jet engine that you mount all of the turbine blades on is still commonly made from steel, which needs to be extremely high performance material. So there's a huge range of applications.
So who's got some questions for Lucy about steel? Yep, we've got one at the back there.
My name's Sam, I'm from St Ives and I'm 12 years old. I might have misheard this in like a science lesson, but if you mix like, I don't know what element it is, would you make like a steel called Damascus steel?
Oh, so you're asking about Damascus steel. That's quite interesting. Now, Damascus steel is a very high performance steel that used to be manufactured quite a long time ago. And if I'm perfectly honest with you, nobody really knows how it was made. But it is remarkably hard. It holds a very good edge, so it was often used for cutting blades. And in fact, I think that Damascus steel was paid as tribute to Alexander the Great at one point because it was such a finely prized material. Now, there probably wouldn't have been a lot of control over the elements that went into that steel, because typically in the ancient world, when they made steel, it wasn't very good. They couldn't control the quality of it. They didn't necessarily know about getting elements like vanadium or chromium that we would add into steel today. So a lot of the old steel makers, they had to work with what they had. Nevertheless, they managed to come up with some quite extreme examples of high performance materials. And Damascus steel has often been associated with carbon nanotubes. There is some speculation, which is questioned, it's not certain, that actually the way in which carbon was added into the steel and the manufacturing process was able to generate carbon nanotubes, which are present within the Damascus steel. I'm a little bit unsure of the veracity of that, and I'm not sure how much of an effect that would have in reality, but it's a bit of a gimmicky claim. So,
I read recently that there was also associated with a certain ore body, a certain form of ore which they were digging up to make the iron from, and that ran out, and then they couldn't make any more Damascus steel.
Oh yeah, that's quite possible. I mean, a lot of steel around the world, obviously, was just made from what they could dig out of the ground. So there would be very different compositional variations, just dependent on the geology of the area.
Kate, do we have a question from Facebook?
Yes, talking of carbon nanotubes, Jae-hyun Hwang asks, carbon fibre and carbon nanotubes are materials with lots of potentials. I wonder how those kind of materials are being applied to your area you've studied for, and if you can think of any commodities, let's say 20 years from now, that might have been made from carbon nanotubes and carbon fibre.
So are carbon nanotubes and carbon fibre going to take over from steel?
Right. I have to be careful not to be too rude about this because it's well known in my field that if you insert the phrase nano into your research, you get a lot more grant money, which is why the steels that I work on have now been renamed nanostructured steels. Now, carbon nanotubes did indeed attract a lot of excitement, a lot of interest when they were made because they drew some exceptional claims. People were claiming that they had a strength of 3,000 gigapascals. Now, just to put that into context for you, the strongest steels commonly in use today, excluding the kind of very specialist high-end steels, are maybe about 2.5 gigapascals. So that's a factor of over 100 in terms of difference. Now, what the paper about carbon nanotubes didn't mention is that the carbon nanotubes that they used to measure the strength were 300 nanometers long. That's not very big. And in a structure like that, we have something called a perfect crystal. So essentially, there are no defects in the crystal whatsoever. There are no missing atoms. It's a perfect structure of atoms, each linked to one another in a regular arrangement. Now, steel derives its strength, as I explained earlier, from the atoms all being higgledy-piggledy and not really being able to move for that reason. And that means that you can achieve this strength state in steels of any size. The problem with carbon nanotubes is they derive their strength from being perfect. So essentially the strength of a carbon nanotube is related to the strength of the covalent bonds between the carbon atoms, which are incredibly strong. So you can obtain very high strengths from very small carbon nanotubes. However, as a result of entropy, which says that we will get disorder in a system, if you make a carbon nanotube bigger than about 2 millimeters, it starts to get defects in it, and its strength absolutely plummets. Now, unfortunately, there was a lot of excitement around saying, oh, space elevators, let's make space elevators out of carbon nanotubes, to which the response of the steel community was, we can build a space elevator out of carbon nanotubes as long as space is only 300 nanometers away. Carbon fiber is different. Carbon fiber is an exceptionally interesting material because it's what's known as a composite material. So it's made up of woven fibers of carbon, which are very, very strong, very tough, and when mixed with epoxy resin to make a composite, provide a very lightweight, very strong, very tough material. But it is extremely expensive, and that at the moment is its downfall. It's also a lot harder to recycle than steels, but we are seeing it used in applications where lightweight strength is required, such as racing cars and so forth. Another similar material is Kevlar, which I wanted to mention today because its inventor, Stephanie Korlek, died last week. But that's become a very, very useful example of a composite material used in armor technology. Where carbon nanotubes really come into their own is with their electrical conductivity process, but it's thought that carbon nanotubes offer a lot of very promising potential for electrical transmission, electricity distribution, and so forth. But in terms of strength, I disdain it slightly.
My name's Hannah and I'm from Cambridge. I was just interested, you keep talking about recycling. Is there a limit to the amount of recycling for the types of special steels that you're working on?
Well, I suppose there is in terms of composition, in that it takes quite a lot of work to get the composition right, and a lot of these steels are very sensitive to composition. So I suppose if you were to sort of chuck everything into a big vat, you basically have lost control of your composition to an extent. So certainly where we're looking at tightly controlling the composition, it would be difficult to recycle them. But there are a lot of applications for steel where the composition doesn't matter so much. So yeah, I'm not aware of too much about that. I imagine there might be a problem, but recycling is still very feasible.
That was Lucy Fielding from the Cambridge University Department of Materials Science and Metallurgy. You're listening to a special edition of The Naked Scientists from the Cambridge Science Centre with our wonderful studio audience. Now, finally, we're moving on to Dr. Kirsty Kuo, who's a research associate at the Cambridge University Department of Engineering again. But Kirsty's working on something a little bit different, a little bit, may I say, more out there. Can you tell me about what you're working on?
The field that I'm working in is called climate engineering. It's an idea that has been around for some time, but it hasn't really been talked about because it's quite controversial. And the idea is that we could modify the Earth's climate. So we could make it hotter or we could make it colder. And now, because global warming is such a challenge for us in this generation, we're starting to think about ways that we could make the climate colder so that we could counteract the effect of global warming.
I thought global warming, we're causing that by burning lots of fossil fuels, putting all this carbon dioxide up there. We just need to stop that, find new methods of making energy, and then we'll be okay. You're doing something a bit different, though.
Yes, so our message is that absolutely we have to reduce our carbon dioxide emissions. there's no way we can get around that. It's something that we have to do. But it's a bit like your house being on fire, really. If your house is on fire, you want a fire engine to come and put it out. And that's a bit like if climate change happens, we want something that can have quite an instant effect and quite a big effect. And so we're thinking about this idea of climate engineering. Unlike a fire engine, which the effect is to put the fire out and that's all it does, climate engineering would have lots and lots of different effects. It wouldn't just lower the Earth's temperature, it would also cause changes in rainfall and changes in local climates and also changes in chemistry in the atmosphere. And these changes are really serious, and it's not something that we want to take on without thinking about it and doing research to know exactly what's going to happen.
So how are you going to go about making the Earth cooler then?
So our idea comes from volcanic eruptions. Particularly in 1991, Mount Pinatubo erupted, and it put lots of ash and other chemicals up into the atmosphere. One of the things it put up was sulfur dioxide. These sulfur dioxide particles are really quite small, but they're just a perfect size to reflect some of the sun's light that's coming towards the Earth. And so these particles produced a cooling effect of about 0.5 degrees C for 12 to 18 months after the volcanic eruption. And our idea is that if we could imitate a volcanic eruption, then maybe we could see a similar cooling effect.
I don't really like the idea of imitating a volcano. Volcanoes are quite scary and quite dangerous. I'm guessing you're going to do it in a slightly more controlled way.
That's right. We're not going to go and just blow up volcanoes around the Earth. So the idea is to get some kind of reflective particle, whether it's sulfur dioxide or something else, and to pump it up into the stratosphere and at a height of 20 kilometers, because that's where it will stay for about 12 to 18 months before these particles start to fall down to the Earth.
How on earth do you get it up that high?
Well, there's lots of different ideas of how you could do it. So you could say, well, we've got aeroplanes that fly at about 10 kilometers. There's some very special military ones that can fly at 20 kilometers, so why don't we use those? Problem is that it takes a lot of energy to get the aircraft up to 20 kilometers and get it back down again with a package of these particles. So a much more energy efficient way of doing it is to build a giant structure where we could pump these chemicals up. Now, building a giant tower isn't possible because the strength of the material isn't large enough. But the way we propose to do it is to build a giant hose, and this hose would be held up by a balloon, and the balloon would have to be the size of the Wembley Stadium to hold up this 20 kilometers of hose, and through the hose we can pump these particles and spray them out at 20 kilometers.
And what's the balloon filled with? Is it helium, like a normal sort of party balloon that floats?
It would probably have to be hydrogen because helium is in quite short supply and it's very expensive.
So we've got a giant hydrogen balloon in the sky with a hose, and then how do you get the material to go up the hose?
Well, you have to pump it up. Like when you turn on your hose pipe at home, there's water pressure which is driving the water through the hose. And in the same way, we'd have to supply pressure at the ground level to move these materials up through the hose. The problem is that the pressure is going to be extremely high. Even in industrial applications where they use very high pressures, it's even higher than that. So that's one of the big engineering challenges of thinking about this kind of technology.
And how much of the stuff would you have to put up there to make a difference?
Well, they've estimated that to cause a 2-degree change in the global mean temperature, we'd need 10 million tons of sulfur dioxide. Now that sounds like an awful lot, but once it gets spread around the Earth, it actually turns out to be about 1 teaspoon of material for 1 square kilometre of the Earth's area.
Fascinating. So who's got any questions on that? Oh, we've got lots of hands up already. One down the front to start with.
I'm Freddie from Little Downham. I was thinking, because I watched a YouTube video about ways the universe or world could end. And it included supervolcanoes, which could block out the sky and create another ice age.
Freddie, are you asking Kirsty whether she's planning to end the world?
No, I was thinking, is that the same sort of thing, or is that slightly different?
Yes, yeah, that's exactly the same thing. And so it is quite scary, isn't it? But there was a Mount Tambora erupted about 200 years ago. And this eruption was so big that it caused something that was called the year without a summer. And basically, in Europe, there was no summer that year because of this volcanic eruption. And it led to huge food shortages and famines. And the interesting thing about that year without a summer was that that was the year that Mary Shelley wrote Frankenstein. And so, yes, it is possible that a big volcanic eruption would cause huge problems around the world.
So if in a few years' time you see Kirsty and she's stroking a white cat and asking for £1 million or she'll blow up the world, she could do it.
My name's Arusha and I'm from Cambridge. My question is, would you need to get some kind of international agreement to do this, presumably because it's global temperatures that you're affecting?
Yes, that's one of the huge challenges. So what we've done to date is we've been doing a feasibility study to try and understand the effect of climate engineering. We haven't done any actual experiments, and that's because of the international agreement that you would need. There's a lot of discussions that are going on as to how you would get this international agreement. It's not really clear how that would happen and whether it would ever happen. And so there is a fear that someone could decide to do this on their own, and it would affect the whole Earth. But hopefully we'll never get to that stage.
David?
So I'm a bit concerned about acid rain. So you put sulfur dioxide in the atmosphere, when it rains, you wash all this sulfur dioxide out, and that's sulfuric acid.
Yeah, so acid rain is one of the problems with sulfur dioxide. One of the other major problems is that it destroys ozone, and so it would essentially destroy our ozone layer. And that's why part of this research project is to look at different types of particles and to see if there's a better particle that we could use that wouldn't have the same effects on stratospheric chemistry.
My name's Sam, I'm 12 and I'm from St Ives. And you said there'll be a big balloon the size of Wembley. What if there was a thunderstorm?
That's a great question. Now, most of our weather happens much closer to the Earth than 20 kilometres. And so it's unlikely that the balloon would get hit by lightning. But it's very likely that the hose could get hit by lightning, because basically we've just stuck a giant lightning rod up into the atmosphere saying, come and hit this thing with lightning. And so that is something that we have to think about, and whether we make it out of a non-conducting material to try and reduce that effect, or whether we have to take other measures to try and reduce the possibility of it being hit by lightning or somehow manage that.
My name's Peter from Cambridge. I was wondering, could you try it out first by pumping ozone into the ozone layer before trying out sulfur dioxide?
That's it. That's an interesting idea. Well, I think however it gets tried out, it's going to have to be very carefully managed, because once you disturb the atmosphere, it's not just a single point that you're disturbing. It's because of the winds that travel around the Earth, you're going to be disturbing the whole climate. And it's also very difficult to know what effect pumping anything into the atmosphere has, because I can pump it in here, but then how do I know if the rainfall in India has changed because of what I've done or because of some other process? And so that's one of the real challenges with how could you test this type of engineering technology.
I'm Helen from Cambridge. So the idea is to lower the temperature, but obviously some places temperature's been lowering and that's not a good thing. Well, that would make it worse in some places and better in others.
Yeah, that's absolutely right. So climate engineering will not be a win-win situation for everyone. It would cause a global mean temperature drop, but some places will get hotter, other places will get cooler. Also, the rainfall patterns will change, so some places will get less rain, some will get more rain. And it doesn't solve all the problems of climate change even, because there's ocean acidification, because we have more carbon dioxide in the air, it's becoming dissolved in our ocean, it's destroying coral reefs and things like that. And climate engineering wouldn't fix ocean acidification. So there are many cons to this type of technology, and it's something we'd have to think very long and hard about before we decided to do something like this.
Kate, you've got one final question.
Yeah, from me. So, Kirsty, everyone's been saying, oh, there's a problem with this and it will raise the temperature and it might destroy the ozone. There's so many problems with this. Why are you still doing it?
It does keep me awake at night thinking of all the problems with this kind of technology. Basically, we're worried that one day we might get to a point where doing nothing is no longer an option, and doing something to lower the global mean temperature, despite what the side effects are, whether they're known side effects or unknown ones, it might be something that we accept because the situation is so dire.
Well, that's about all we've got time for this week. I want to say a huge thank you for all our guests, David Cardwell, Sinan Achikos, Kirsty Kuo and Lucy Fielding. Also, if you want to join us next month, we're going to have another special Science Centre edition here at the Cambridge Science Centre. And this time, because it's summer, we thought we would take a metaphorical trip to the seaside and talk all about the marine environment. The Naked Scientist comes to you from Cambridge University and is supported by the Wellcome Trust, the STFC and the EPSRC. I'm Ginny Smith. Thank you for listening and goodbye.